So but I've got actually two posted both at the same time this time around. So, I need to double check and make sure they program us correctly, but we have Columbus Day weekend coming up. And so in having Columbus Day weekend coming up, JCC is not in session on Monday, and so we don't have class next Monday. But JCC, in its infinite wisdom, needs to be able to document to the state and everybody else that we meet the right number of minutes in a semester. And so when we return next Tuesday, which is I think the 13th, JCC will be running a Monday schedule. That means we meet next Tuesday morning. So just to remind you or to let you know, if you have Monday, Wednesday, Friday, JCC Interactive TV classes, we generally meet next Tuesday at the regularly scheduled time. And then the rest of the week is a normal week. Wednesday's Wednesday, Thursday's Thursday, Friday's Friday, which means we actually meet next Tuesday and Wednesday. So we have kind of a little goofy thing that occurs here on campus. So I'll remind us of that on Wednesday. I'll post something about that. I'll try to remember to actually send something to your schools. I need to double check and make sure they hook up the technology, et cetera, et cetera. I'll say this also again, but the following week, October 19th and 21st are 2 days that our class meets. The 19th, you will have an exam. So I'll keep telling you that. So the 19th, we'll have our second exam. Normally, I'd want to have it next week, but I am actually not here either the 19th or the 21st. I'm away at a conference. And so we're going to have an exam on the 19th because I can have you proctored and you don't necessarily need me as long as I'm careful and don't have errors on the exam. And then the 21st, we will not meet. And what I'm going to ask is to have your schools have you come on Friday the 23rd. So we're going to have a little, we'll have a little change in schedule. I'll put an announcement in Blackboard and I'll send some information to your schools that's on all of that. But it's we're going to have a little kind of goofy time period coming on here. So again, I'm recording today. There's a couple of folks who aren't here. Helps out a little bit with that piece. So there's kind of the game plan for right now. Hope you all had a nice weekend. I'm sure just any time that's away from school, right? Some of you probably had some athletic contests. I actually spent most of my Saturday here at JCC. My husband was off driving a bus. He drives bus for Rob Freeman here in town, or Clarence Henry Coach, the weight coaches. And so he was off taking the IHC football team down to Lafayette on Saturday. So I came to JCC and I watched women's soccer, men's soccer, and women's volleyball here on campus. So kind of a neat time to do that. So I apologize that Alex Bay can't really necessarily speak to me today, so that means that everybody else has to talk to me, which really probably is like, okay. So what I do want to do today, though, maybe we'll wait on some of the homework piece until the Bay hopefully can talk to us on Wednesday. Maybe I'll wait to go over some of the Chapter 3 material, and in terms of homework questions and that type of thing. And instead finish off some of the Chapter 3 material, and I want to do a little introduction to the beginning of Chapter 4. So remember, Chapter 3 only has 2 sections. And so in that process, that means that we'll be actually entering Chapter 4 today. So, let me get out my stuff here. I've had one of our tech people kind of keeping an eye on this, so I think it's time now that we can get going on the rest of the math. I wasn't sure if they were going to do something to the connection this morning or not. So, there's one piece that's left in chapter 3 that I want to make sure that we spend some time on before I introduce a little bit with chapter 4, and then we'll spend a lot of time. I'll pretty much just do a bunch of problems on Wednesday from chapter 3 and the beginning of chapter 4. So I want to refresh our memory on a technique I think at least some of you have seen before, and it's the technique of completing the square. I'm going to break this up into two different parts in terms of completing the square. One is what, if you've seen it before, you typically have, using the completing the square to solve an equation. And the second is using the completing the square to rewrite a quadratic function in what we talked about last time as vertex form. So we're going to do completing the square. I'm going to do item 1 first, completing the square to solve an equation. And then I'm going to modify the process just slightly to complete the square to rewrite a quadratic function in vertex form. So let's do, we look at item 1, and you'll want to really pay attention to the differences between the two things that we do, because it'll mess you up if you don't pay attention. So item 1, I'd like to do something like solve x squared plus 6x plus 2 equals 0. And I'm going to solve that by completing the square. If you tried, this doesn't factor. And so typically, if I were you, I'd probably be using the quadratic formula, but I want to actually do this instead of the quadratic formula by completing the square. So let's just do a quick little check at Alex Bay. It's always kind of goofy. By the way, for those of you that may not have popped in here, their front screen doesn't work, which is why I get to look at the back of their heads today. But that's okay. I can cope with that. So at Alex Bay, I need kind of the thumbs up or the thumbs down. Do you recall completing the square before? Okay, yeah, we have. How about at Copenhagen? Do you remember the phrase completing the square from before? Yep. Sackets? Yeah. So if I ask this question, I'll let my schools help me out here a little bit. If I ask this question, so I want to solve this by completing the square. The first thing I'm going to do, and I'm going to start us off, and I'm going to ask you about the actual completing the square. So I'm going to solve. I need to get the number on the other side, the non-x term, the constant term. So in this case, that gives me a -2. Then I do this thing called completing the square. Since you're familiar with it, how do we figure out that completing the square piece that we need? Remember the math?
Divide the middle term by 2.
Divide the middle term by 2. So I'm going to divide the middle term, and by middle term you mean the x term. So I'm going to take 6, divide it by 2. And then is there something else I do?
X plus 3.
Yep, that's 3. And then I do what with the 3 I heard somebody say? Square it, yeah. So I take half the b term and I square it, and that's what I need to do to complete the square. So I take half that b term and square it. And then once I have that number, and I'm going to do this in little extra steps, so it kind of appears if you follow my notes that you'll have kind of the step by step. Then we take that number and we add it to both sides, don't we? Why do we add it to both sides? Gotta keep the balance. Yeah, gotta keep the balance. Now, by completing the square, the nice part is this left-hand side should now factor into a perfect square. Right? We should end up with the same thing written down twice. And in this case, it's x plus 3 written down twice. Or in other words, x plus 3 squared equals 7. Now, my goal is to solve, so now what do I do to solve this? Probably up at Alex Bay, they're like yelling the answer and we can't hear them. So what do we do? What do we do to solve this? No takers today, huh? How about taking the square root of both sides? Do you remember doing that? I don't like to talk to myself, please. So we take the square root of each side. And remember, on the constant side, we have to use the plus or minus because there's two roots. That's what's going to get us the two solutions. And then the square root and the square do what?
Cancel out.
Yeah, they cancel out. And they cancel out because the function of square root and the function of squaring, under certain circumstances, are inverse operations. We have to be a little careful with the use of inverse, but they really are inverse operations. And then the last thing we would do is we would move the 3 to the other side, solve for x. So we get negative 3 plus or minus the square root of 7. Right? So that's the most basic of the completing the square techniques. Now, unfortunately, the mean math teacher doesn't usually give them that are quite that simple. Usually I do one of the other situations that can happen. And so I'm going to do two others, and then I'm going to do the other situation. We'll do an example or two on the other situation. So suppose I wanted, again, I'm going to use the completing the square, and I want to solve negative x squared plus 8x minus 3 equals 0. This one's trickier because notice that the a term is not 1. Where in the previous circumstance, the a term was 1. Now, if it's a solved problem, if you wanted the a term to be 1, we could probably move everybody to the other side of the equation. But I'm going to pretend not because I need to be able to do it in this form for the item 2 process that we're looking at. So again, I do exactly the same thing when I'm solving that I did before. I get the constant term on the other side of the equation. So again, I'm keeping that negative because I want to show something with this technique. So I move the constant term to the other side, and just like you told me before, I complete the square on the b term. So I take half of 8, or I divide 8 by 2, and square it, and that gives me what number?
16.
16. And then what did we say we do with the 16?
You add to both sides.
Add it to both sides. Thank you. So again, I'm writing out the extra step just so that you can see the open space followed by the adding the 16. Now, I have a little problem. Because this doesn't factor into two strings. And so what's happened is the math teacher's taking you down the wrong path. I did that intentionally. Because now, notice if I just do what I did here, I don't have a perfect square trinomial. I can't write this as x plus and x plus. Now, if I'm a little bit funky and fancy, I can rewrite things and I can get it into that format. So I might be able to do something a little fancy. But unfortunately, if I follow the exact set of steps I did here, this no longer goes into this situation, and that's because this minus is messing me up. So the mean math teacher said, hey, let's try this. And then the mean math teacher says, when the negative is there, that doesn't work. And I did that intentionally because I wanted to do what typically students do. In some ways, messing up your notes, but it's kind of a mess up your notes to notice that this doesn't work. And so what I have to do is I have to punt and do kind of a second set of steps instead. And what I have to do when this a is not 1, and in fact in this case, notice it's really -1, is before I complete the square, I have to actually factor out that number. And so what I'm going to do, when that a is not 1, what I'm going to do is factor out that a value from what I'll call the a and b terms. You will notice even when I do approach 2 that I will only be factoring that a term out of the a and the b terms. Never the constant term. Never, ever, ever the constant term. Only the a and b terms. So now if we go and we do this the right way, I'm going to factor a -1 out of those 2 terms on the left-hand side. So if I take a -1 out of x squared, that just leaves me with x squared. Now here's the tricky part. If I take a -1 out of 8x, out of a plus 8x, what does that leave me with?
-8x.
A -8x. So notice I don't touch the right-hand side, and I haven't messed up the balance of the equation. I haven't done something to one side that I didn't do to the other side. The left side is exactly the way it was before. I've just rewritten it. Now I can complete the square. And technically I'm completing the square on -8, but I still end up with the same 16 that I had before. That squaring always gives me a positive. And so now, inside the parentheses, just like I did before, I'm going to put a plus 16. Now, here's the question. What number goes on this side? -16. Why -16? And these two together actually have the net effect of subtracting 16 instead of adding 16. Those two have the net effect of subtracting 16. If I multiplied that back out, it would actually look like I had subtracted 16. And to maintain the balance, I'd have to subtract 16. So I have to do the same thing to both sides. So notice, the effect here is subtract 16. So no, my effect was subtracting 16, and so that's why I have to subtract 16 on both sides. Left side still factors. This time it factors into x minus 4 squared. And notice I keep the negative 1 out in front. So I'm going to have a negative 1, and then when it factors, it's an x minus 4 and an x minus 4. The right side gives me a minus 13. Now, if I went to the previous example, this is the point in time where I actually took the square root of both sides, but I'm not going to here. I need to get the square part by itself. So I'm going to divide both sides by that coefficient, by that negative 1. Which is nice because that then gives me a positive number on the other side, which is what I prefer to have. Now I'm back to the basic boring thing I did at the end of the previous example. Take the square root of both sides. But don't forget the plus and minus. So x minus 4 is plus or minus the square root of 13. So x is 4 plus or minus the square root of 13. So notice the trick here, when the a isn't the number 1, what we need to do is move the constant when we're solving, move the constant to the other side, but then factor out that. Now again, when I'm solving, there are some other ways I could deal with that. I could just start off right at the beginning and divide everybody or multiply the whole thing by negative 1, or someplace along the line do the same thing. But I did it in this way on purpose because of where we're heading. So I'm going to do one more solve by completing the square. And then I'm going to do the second technique, or the second item. So this time I'd like to solve 2x squared plus how about 16x minus 3 equals 0. This time again, notice my a term is, the a number is not the number 1. So approach is still the same. I won't send us down the wrong path this time, I promise. But the approach is still the same if I'm solving. I still get the number, get the constant term on the other side of the equation. But just like I did in the previous example, before I complete the square, I'm going to factor out this a term. That's going to be what's going to be critical in both of these techniques. If a is not 1, I'm going to have to do this factoring out the a term. And again, I do this, I will never, ever, ever in this approach, ever factor it out of the constant. The constant gets left alone even when I do the other process. And half the middle coefficient, half the b term, half of 8 is 4, 4 squared is again 16. I like 16 today. Add my 16, this time inside the parentheses, similar to what I did before. Probably should change this one. You know, I'm gonna cheat. Hopefully, I won't mess your notes up too much because I don't want to have this happen. I'm going to change that 3 into a 35. How's that? So I just changed it all into a 35. Just makes my life a little cleaner. So, what was my net effect? What did I do on the left-hand side? What actually occurred? Yeah, and so that 2 and that 16, they actually end up giving me a 32, don't they?
And then on the right side, you have to subtract 32 to the 35.
You sure?
I thought I was, but apparently not.
Well, let's do that. You might not want to write this down yet, but let's do it. Because I'm actually glad that you did that, because that's what we're going to have to do in a couple of minutes. So that's good. We can kind of talk about why we do what we do. If I subtract the 32, let's just go over. I'm going to do a little thought bubble here. This is the Jerry Fairman thought bubble. If I multiply this all back out, I go backwards. This would be 2x squared plus 16x plus 32 equals 3. Right, so I just did the math. And if I bring the 3 back over, that's 2x squared plus 16x plus 29 equals 0. So all I did was I multiplied out what you gave me. By trying to go backwards, am I back to the original question? Am I back to where I started?
No.
No. So, I'm glad you did that, because like I said, in just a couple of minutes, that's exactly what I'm going to do. But when I'm solving, what I do to the left and what I do to the right are the same. So if I add, if it ends up the net effect of adding, I have to add again. Notice if I go back here, my net effect was subtracting 16. So my net effect here was subtracting 16. So notice I did a subtract 16, subtract a 16. So I didn't add a 32, I add a 32. But that's only with the solving. I'm making a real point of that. So instead of getting that, I'm going to have the number 67. I want a nice big number here, because usually I end up with all these little tiny numbers. And then this factors, I keep the 2. And I have x plus 4 and x plus 4, or twice x plus 4 squared is 67. Again, to solve this, I need to get rid of the 2, which gives me the very ugly 67 over 2. And then I take the square root of both sides. This comes out pretty. Some of you might actually want to do kind of the come out pretty. Right, 33.5. And remember, take the square root of that side, plus or minus. So x plus 4 is plus or minus the square root of 33.5. Your book is not big, doesn't really matter whether we do a bunch of rationalizing stuff or what we do. So this is going to be acceptable since that came out neat. And so x is negative 4 plus or minus the square root of 33.5. Now, I just went through in gory detail solving a quadratic using completing the square. Probably spent more time than I could or should have, because it's really the next technique that's going to be important to us for where we are. But I wanted to do these because this is more of what you've seen. So let's go into what the textbook really wants us to probably spend time on, because I'm going to tell you quite frankly, and I'm running away to sharpen my pencil here. I'm going to tell you quite frankly, I would probably never use completing the square to solve anything. I'd probably use the quadratic formula if I couldn't factor, but, you know, it's kind of a fun little process once in a while. So now what I'm going to do, though, is use completing the square to rewrite a quadratic function in vertex form. And so remember, when I say vertex form, that's going to look like y equals, or f at x equals, a times x minus h squared plus k. So what I'm going to be doing is I'm going to be taking something of the form ax squared plus bx plus c, and I'm going to be converting it into that form. And I'm going to be using completing the square. So I'll do the easy version, then I'll do like the, well, I won't call it the hardest version, because I'll make sure I do one that doesn't have fractions in it. That would be the hardest version. So suppose I have y equals x squared minus 10x plus 7. And I want to rewrite that in vertex form. And I'm going to use completing the square to do that. I'm going to do this problem without moving the constant to the other side. So when I solve an equation, I move the constant to the other side. I'm going to do this one without moving the constant to the other side. So what you're going to see I do is all I do is I move the constant down. So I just move that constant down out of the way. By not moving it to the other side, that's where I'm going to do what we kind of looked at the last example as the add and subtract technique. I'll do the opposite. Now what I do is I complete the square on those first two terms, just like I did before. So x squared minus 10x. What number do I get when I complete the square?
25.
25, yeah. So I'm going to add 25. And now instead of adding 25 to the other side, I'm going to do the opposite. So now I'm doing an add and subtract, and so it's like I stuck some additional weight on the scale and then I took the same amount of weight off the scale. So in this process, instead of doing something to the other side, I'm going to do it all on the one side of the equation, and so if I add, I'm going to subtract. If I subtract, I'm going to add, if that net effect. Now resist the urge to combine all the numbers together and just take these first three and factor them. And they factor into x minus 5 squared. And then I combine the 7 and the minus 25, and that gives me a negative 18. The neat part is I should be able to multiply that out and get back to the original. These two should be equivalent. They should be equal to each other. Once I have done that, now I am in vertex form. Since I'm in vertex form, I should be able to tell what the vertex is. So let's test what you remember. What's going to be the coordinates of the vertex? You were kind of quiet. Can you say that again?
5, -18.
Thank you. 5, negative 18. Remember, it's always the opposite of what we have here, and exactly what we have here. It's x minus h, so it's, yep, so it's 5, negative 18. just to test ourselves, what would be the equation for the axis of symmetry?
X equals 5.
Very good, thank you. X equals 5. Notice, by the way, don't forget you need the x equals. I get some students that get so excited about the 5, they forget the x equals. We'll do one more. We'll do kind of the ugliest that they get. And then I'm going to talk a little bit about the beginning of chapter 4 for a few minutes. So, negative 2x squared minus 24, oops, x. I always want to drop the x off. Minus 2x squared minus 24x plus 25. So again, we're going to do the same thing. And so again, that process that I'm using says move the 25 out of the way. And so until I get to almost the end, I'm not going to touch that 25. Now notice here that again, like some of the other examples, the A is not 1, where the A was 1 up above. So what do you suppose I do if the A is not 1?
Factor out the negative 2.
I am. Now, do I factor the negative 2 out of the 25?
No.
No. So I only factor the negative 2 out of the first two terms. If I factor a negative 2 out of negative 2x squared, what does that give me? X squared, yep. If I factor a negative 2 out of minus 24x, what does that give me? Plus what? 12, yep, plus 12x. Now I complete the square inside the parentheses. So again, it's half of 12 squared. So half of 12 is 6, squared is 36. Now the question is, what do I do on the end? Well, what was the net effect? If I were to multiply that back out, what's the constant number that I get from these two? Negative 72. So my effect so far is that I've subtracted 72. Since I'm staying on the same side of the equation, I need to do the opposite of that. And so what I need to do is add 72. So what I actually have done is I've done a subtract 72, and and then I do an add 72. So that's going to give me a lovely and charming 97. And then this is going to factor. It's going to factor into x plus 6 times x plus 6, or x plus 6 quantity squared. And then I'm done, and I can find the vertex and the axis of symmetry if I wanted to.
So in this kind, you don't go any farther than that?
No, on this kind we won't go any farther than that. That's an excellent question. If it's just asking us to rewrite in vertex form, We just stop right there. Excellent, excellent question. Sometimes they ask us to go further and that they'll ask us what's the vertex and the axis of symmetry, but that would be the extent of it. So that's the last little bit. And again, even though I know you told me you did completing the square, my experiences, and I remember it when I was a student, my experience is that you weren't very confident with it before. And that it's one of those that the cobwebs are kind of dusting around and running around in your brain. And so I tend to do this because if I leave you to your own devices to refresh your memory, it doesn't go well for any of us. I know things that I can talk about quickly, and I know things I better spend 35 minutes on. So that wraps up what we would talk about in Chapter 3, and it lets us talk about, move into talking about what becomes Chapter 4 and Chapter 5. Chapter 4 and Chapter 5 kind of go together, and they are everything we want to know about one topic that you usually like, exponential functions, and one topic that I usually get mixed reactions on, logarithmic functions. So we're going to spend a couple of weeks here, probably 3 weeks or so, talking about exponential and logarithmic functions, and then we're going to spend almost the rest of the course talking about trigonometry. So that's kind of where we're heading here. There's a couple of other topics that are in there, but we're going to spend a chunk after that. So, we won't worry about logs today. Don't even go, oh, logs. They're really Chapter 5. So we're going to talk a little bit. I want to introduce in 10 minutes a little bit to do with exponential functions. I'm going to do a little bit of just recalling what we know. So, exponential functions are things of the form y equals, and depending upon the format that you're used to seeing, they either look like a times b to the x. There's a couple of different, I'm not going to do one of the versions, or sometimes you'll see y equals b times a to the x, and again, there's some other formats that are out there. Your textbook will put the letters initially in that format. Why am I making a point about that? Well, in this particular format, the a, the item not raised to the power, and notice the a is not raised to the power. A is always going to be greater than 0 in the processes that we're going to do early on. If we did negative, we're talking about some other kind of stuff that comes along in terms of shifts and reflections and that type of thing. For our purposes, A is going to be greater than 0. And A is actually, I'm going to use in this language, A ends up being the y-intercept. And why do I make a point out of that? We're so accustomed from our lines that it's the B is the y-intercept when we see the B in there. But it's the A in this case, written this way, that's the y-intercept. If we actually wrote it in this form, it does end up that B is the y-intercept. But your book is going to use this particular, much more of that particular form. The B is called the growth factor. And you will notice they always use, when they start using the language, they always use the term growth. But what actually happens is if B is greater than 1, we have growth. And if B is between 0 and 1, and again, B won't be negative, we have decay. But the general term is that no matter what, B is the growth factor. It's just sometimes your growth is actually decay. So how did these operate? Well, kind of the example that I often will use is, suppose I have $1,000 and I'm going to invest that $1,000 at, say, 3% per year. Certainly not in a bank account nowadays. It has to be in something a little more risky to get 3% even. So I have $1,000 and I'm going to invest it at 3% per year. I'm going to be using T instead of X here just to warn you. So at T equals 0, I have $1,000. So at the start of time, I have $1,000. After 1 year, and by the way, I'm investing only one, or I'm putting the interest on only one time a year. I'm making this oversimplified. After 1 year, I'm still going to have my $1,000. It's in something I can't take it back out. So I'm still going to have my $1,000, but I'm going to have some interest, and I get that interest by taking my 1,000 and multiplying by 3%. And I could do the math out, but I don't really want to do the math out. What I want to notice is, if I do a little bit of algebra, if I go back to my algebra, I could actually factor out 1,000, and if I factor out 1,000, that gives me 1,000 times 1.03. If I take out 1,000, it leaves me with a 1 on the first 1,000, right? That's as if I'm multiplying by 1. And then a 0.3 from the second. So I have 1,000 times 1.03. In year 2, at the end of year 2, I have all the money I had before. So what I had from the previous year is that 1,000 times 1.03. That's always my starting amount for the next year. But then I'm going to take 3% of that. So I always have my starting amount, and I take 3% of that. And again, if I factor out what's common, I'm going to factor out 1,000, and this time I'm going to factor out a 1.03. And when I factor 1,000 times 1.03 out of the first, I have another 1. And when I factor it out of the second, I have another 0.03. And what I notice is I get 1,000, when I do the math out, times 1.03 squared. I probably don't have to do this very many times. You're all really intelligent human beings to recognize that if I had T equals 3, by the time I got done, I'd have 1,000 times 1.03 cubed. And if I generally had, instead of a 3, if I had some generic thing like an n, so it's n years, I end up having 1,000 times 1.03 to the n. So I can figure out how much I had in 20 years. I wouldn't have to do this out 20 times. I would just put the 20 in. Notice when I do this, I can kind of analyze this a little bit. Notice that 1,000 was my initial investment. And notice this 1.03 actually was 1 plus the interest rate as a decimal. Notice that number is 1 plus the interest rate as a decimal. And that 1 plus R is another way to write the B, the growth factor. So now I'm going to make a quick change in name and notation. So remember, B, the whole number, is the growth factor. And this is what always confuses students. The R that I gave you, that 3%, is called the growth rate. So we're going to have two words going around here. There are two phrases that are going to mess you up. Growth rate and growth factor. The growth rate is usually given to us as a percent, and the growth factor is not always given as a decimal, because I can make some changes to what we would be saying, but the growth rate in a problem is typically the percent that's given. If, I'm flipping my page here, if we have growth, that B that's in our formula becomes 1 plus that growth rate. But if we have decay, B ends up being 1 minus the R. So, a couple of real quick examples. If my initial value is 500, and I'm growing by 2% per year, then the equation becomes y equals 500 times 1.02, and I'm going to use a t because I have time going on here. So if I'm growing, I do 1 plus that. If my initial value is, say, 600, and I decay by 5% per year, then the formula becomes y equals 600 and 1 minus 0.05 to the t, or 600, and you might want to pull out your calculator because students mess this up all the time, times 0.95 to the t. So if you do the decay, you do 1 minus. If you do the growth, you do 1 plus. Okay. Well, that's where I'm going to let off because it is 5 of. And so make sure you go out on Blackboard, take a look at what the work is that you're supposed to be doing. I'm going to have you starting off chapter 4. I'm going to spend basically the entire class next time finding out if there's stuff from quadratics we still want to talk about. And then I'm going to take a look at the first couple of sections of chapter 4 and do a bunch of problems. So it's going to be a problem day. Hopefully we'll have the volume back because I'd rather have the volume back to be able to talk to Alex Bay and go through a bunch of problems. I don't mind lecturing a little bit more when you can't speak to me, but I really prefer if you can speak to me that we can kind of go that way. So have a great day, and I'll see you on Wednesday.